Here's an interesting word problem. Suppose that we have a wire that's 10 meters long and is going to be cut into two pieces. One piece will be shaped as an equilateral triangle, meaning that the lengths of the sides of the triangles are all the same, and the other piece will be shaped as a circle. I want to express the total area enclosed by the pieces of wire as a function of the length x of a side of the equilateral triangle. After we do that, I want to figure out the domain of the area, and I want to graph the area function and find the value of x for which the area is the smallest. Let's start by drawing a picture. So we have this wire that's 10 meters long. Just get an idea of what it looks like. Let's say this is the wire, and this length is 10 meters. Now we're going to cut it into two pieces. So let's say we cut it, I don't know, maybe here. So we're going to have this piece. Let's call this P1 for piece 1, and this piece is P2. And with that first piece, I'm going to bend it and make it a triangle. So equilateral triangle. And that's using the P1 piece, so we bend it like that. And then with the P2 piece, we're going to make a circle. We want to express the total area enclosed by the piece of wire as a function of the length of a side of the equilateral triangle. Okay, so how do we find the area? So the total area enclosed by this wire, well, the whole wire, right? So it's enclosed by this equilateral triangle and the circle. Well, we need to figure out what the area of an equilateral triangle is. So remember that the area of a triangle, let's write it up here. Area of a triangle is 1/2 base times height. And the area of a circle, that's equal to pi r squared. So this is an equilateral triangle. Let's label the sides. We want the length x to be a side of the equilateral triangle. So let's call this side x, which because it's equilateral, this side is also x, and this one is also x. So in other words, the perimeter of the triangle is 3x. We also can find the perimeter of this circle, but we need to know some information about this, the lengths of these pieces. So how long is P1? Well, remember we took that piece P1 and we bent it to make this equilateral triangle. So this P1 has length 3x. Whatever x happens to be. So if this was 2, then 2 plus 2 plus 2, 2, 4, 6, this length would be 6. Then what would this length be if this length was 6? Well, the whole thing is 10 meters, so it would be 10 minus 6. But because x is a variable here, this length is going to be 10, the whole thing, minus whatever this length is, which is 3x. And this 10 minus 3x is how we made the circle. So we're going to bend that length to get the circle. And that's going to be the perimeter of the circle. So let's put that down here. The perimeter of the circle is equal to 10 minus 3x. We want to find this area function, and so the area in fact, let me do this in a different color. Let's put it in red. The area enclosed by the wire is going to be equal to the area of the triangle plus the area of the circle. Because we want the whole area enclosed by all of this wire, and part of it was right here and part of it was right here. So we're just going to add these two areas up. So it's equal to, well, we said 1/2 base times height plus pi r squared. But the thing is, we want to take this, now this is the area enclosed by the wire, but we want to write this area as a function of just the length. So we want to get rid of the b, the h, and the r squared. Those are variables here. This pi is a fixed number, and we just want to have x's here. So anything that's a letter needs to be replaced with something involving an x. So let's see if we can do that. Well, let's start with this triangle. We know that the area of the triangle, we said, is 1/2 base times height. Well, what is the base and what is the height? So let me erase this. So if the area is 1/2 base times height, the height is this length that's perpendicular from the base. So this is the base and this is the height. How do we find this length? We know this length because that is the bottom of the equilateral triangle, which is just x. So b is going to equal x in this equation, and we can actually just erase this b and put an x here. So at least we got rid of one of the variables. What about the height? How can we find this? Well, notice that this is x, the side here, and this height intersects this length of this the base here right in half. So this piece is 1/2 x, and this piece is 1/2 x. So by doing this, we can focus on this half of the triangle. This half, this is a right triangle. So if we zoom in right here, or just redraw it here, this is 1/2 x, and this is x. And this is the height. And I need to figure out how to write the height in terms of x and this 1/2 x. Well, because we have a right triangle right here, half of it is a right triangle, we can use the Pythagorean theorem, which says for two sides, here's the two sides, if we square them and add them together, so I'm taking this side and I'm squaring it, and taking this not this side, and square that, I'll get the hypotenuse squared. Right? These are the two shorter sides. They're always the legs of the triangle, and this is the hypotenuse. And it says, square this one, square this, add it together, you get this one squared. So using this equation, we can solve for h. So I'm going to move this 1/2 x squared to the other side, and I get that h squared is equal to x squared minus 1/2 x squared, just like that, right? Solving for this one by moving that one to the other side. I'm going to clean this up a little bit. This is h squared is x squared minus, now this 2 is going to be distributed to both, so this is 1/2 squared x squared, or in other words, h squared is equal to x squared minus 1/4 x squared. Okay, and then from there we can combine these two, because this one is 4/4, because the coefficient is 1, I can write it as 4/4. So 4 over 4 minus 1 over 4, that's 3/4. So h squared is 3/4 x squared. And now I'm going to take the square root, because what I'm trying to do is replace this h here. So if I take the square root, I get h is the square root of 3/4 x squared. Now I don't have to take the negative square root because this height is a length, so we're not going to worry about the negatives. Okay, we're almost done. We can actually go ahead and send this square root into everything. So h is going to be the square root of 3/4 times the square root of x squared. And x is also a length, so this is just going to simplify to, we can say, the square root of 3 divided by 2, taking the square root. So this breaks into the square root of 3 over the square root of 4, which is 2 times x. So that is going to be the height of our triangle. So I'm going to erase this h, and what I'm going to do is I'm going to put, instead of h, I'm going to put root 3 over 2, root 3 over 2 x, because that here was b, here was h. So I'm replacing it with this answer that we found. Okay, so now I've got this, that the area is equal to 1/2 times root 3 over 2 x squared plus pi r squared, which we can simplify to root 3 over 4 x squared plus pi r squared. Now we need to get rid of this r. And how we're going to do that is using this piece right here, the perimeter of the circle and the area of the circle. So let me erase this so we have some room. So how can I get rid of r using the perimeter? Well, we have to recall what the perimeter of a circle is. So the perimeter, the formula of a circle is 2 pi r. And because we know that the wire, the length of it is 10 minus 3x, we can say that 2 pi r is equal to 10 minus 3x. And we can solve for r by dividing both sides by 2 pi. And that should be a 3 right here. 10 minus 3x divided by 2 pi. So this is r, which tells us we can replace the r right here. We need to square this, and we'll get that the area is root 3 over 4 x squared plus pi times this one, 10 minus 3x over 2 pi squared. And I'm going to clean it a little bit further. I'm going to distribute this 2 to the numerator and the denominator. So the area on the top, I have 10 minus 3x squared over 2 pi squared. But 2 pi squared would be 4 pi squared. So let's erase this and distribute this 2. And I can go one step further. I can get rid of this pi because I have a pi down in the denominator. So this and this will just simplify to pi on the bottom. And what I'm left with is that the area enclosed by the wire is root 3 over 4 x squared plus 10 minus 3x squared over 4 pi, what's left on the bottom here. And notice that this area function is a function that just has x's. There's no other variable. So we can define it. We can let a stand for area, and we can say a of x is equal to this right here. Now you can FOIL this out if you want to. I'm just going to leave it like that. I think it looks nicer than the full FOILed out version. But this is our area function. So that's what we wanted to do here. So it says express the total area as a function of the length x of a side of the equilateral triangle. So we're done with that piece. Okay, let me erase some of this so I can see the problem. We can move this up to answer the second part of this. So that was a little tricky. Let's see what we need to do with this second piece here. We want to figure out the domain of the function a. Now let's look at this function. This function, you can see that the x's are in the numerator. I have an x here and I have an x here. And there's no x's in under a square root. There's not an x in the denominator. So if I just gave you this function, you would say, oh, this is, the domain is all real numbers, which is true for the function, but for our problem, not necessarily. Because, for example, this length x, it is a length of a side of a triangle, and triangle sides cannot be negative. Remember this length x? Well, there's no such thing as a negative length of a triangle. So first off, x definitely has to be greater than or equal to 0. Now remember how we made x, these lengths of this triangle. We cut a 10-meter wire. We made some kind of cut, and this piece right here was 3x. Now the domain of a function is all the x values, what you can plug into your function. So first off, we said that in order for this to be part of a triangle, we have to have x is greater than or equal to 0. But there's actually an upper limit as well, because this length 3x, right, it cannot be bigger. So let's say x was, for example, x is 1. We'll get 3. 3 times x is 3. So that's saying that each one of these sides has a length of 1. But if x was, let's say, 5, for example, this is not going to happen because 3 times x is 15. And 15 is bigger than the 10 meters you have of wire. You can't make a side of a triangle to be an equilateral triangle to be 5 meters, each side be 5 meters, if you only have 10 meters of wire. So you can see that there's an upper limit. This 3x here, so 3x has to be less than or equal to 10. In other words, x has to be less than or equal to 10 over 3. Because each one of these was 10 over 3, then you would have a equilateral triangle, and the whole thing, all the perimeter would be 10, and there would be no circle here. So definitely x has to be less than or equal to 10 over 3. And you can see for the circle, the perimeter of the circle we said was 10 minus 3x. And here, whatever x is, you can see if you plug in 0. So if you say there's no triangle, if you let this just be 0 and you take the 10 meters and make the circle, that's okay. You can see that you can't put anything less than 0 here. Okay. If you put something less than 0, you're going to get a number bigger than 10, because let's say you put a -1 in here, this will be -3 times -1, which will give you 13. So that's a problem because you only have 10 meters of wire. You can't put anything bigger than 10 over 3 in here. you can see if you put 10 over 3, the 3's cancel, and 10 minus 10 is 0, which means you would have no circle. So the smallest thing you can put in is 0, and the biggest thing you can put in is 10 over 3. So this is the domain. So the domain, if you want to put it in interval notation, is from 0. We can equal 0 to 10 over 3. Now, if you actually want to have at least an equilateral triangle and a circle, let's say you want to make a cut. So if I'm forcing you to make a cut, if you're going to cut it into 2 pieces, then you can't be equal to 0 and you can't be equal to 10 over 3. Because if you're equal to 0, then you're not making a cut, right? There's no cut. Because you're using the whole wire to make the circle. And if you use 10 over 3, you're also not making a cut, because you're going to be using the whole wire to make the equilateral triangle. So if you want to be very careful here, if I'm forcing you to make a cut, you know you're going to cut it, then you actually can't be this lower end and this upper end. So you would have to get rid of this equal sign. Now, if you want to say, well, you don't necessarily have to make a cut, you can use the wire to form just the equilateral triangle or just the circle, then you can put the equal signs here. Okay, let's graph this. So again, I'm going to use Desmos.com. So again, Desmos.com. And let's go to graph. And let's put this area function. So A is equal to square root 3 divided by 4 x squared plus 10 minus 3x squared over 4 pi. So you can just type in pi for pi. And here's the graph of the equation. Oh, doesn't this look familiar? It looks like a parabola. And it is a parabola. You can see that I have an x squared term and I have another x squared term, which is what a parabola is. It has an x squared term. So this is, we could actually shift the parabola to get this. Now this is a complicated version of the parabola, so we're using this graphing utility to help us graph it. But technically you could use translations and transformations to get your graph. Okay, so the question was, so after we graphed it, find the value of x for which the area is the smallest. Now the y values are the area. So the minimum number is at the bottom of this valley, and you can see when x is 2.077, we get that the area is 2.998, and any other x value would be above this 2.998. So when x is equal to, we said 2.077, the area is the smallest, and that area is actually equal to 2.998.